Thank you, Matthias, and thank you to all of the organizers for the invitation to give this talk here at this wonderful conference. So I want to start with the problem that motivated all the topics of this talk. So the starting point is a Poisson foliation, which is a triple consisting of a regular foliation on a smooth manifold M and a leaf tangent Poisson structure, which is a Poisson structure, which is a section of this vector bundle. And suppose that this Poisson foliation is endowed with two, in principle, independent structures. First, we have a Lie group action, which is canonical and foliation preserving. So the action preserves both the Poisson structure and the foliation, in the sense that the action takes each leaf of the regular foliation to a possibly different leaf of the foliation. And on the other hand, we have a Poisson connection on this Poisson foliation, which is an Ehresmann connection on this foliated manifold, a vector valued one form satisfying these two properties, which is compatible with the Poisson structure in the following sense. For each local projectable vector field, the horizontal part with respect to the given connection is an infinitesimal Poisson automorphism of the Poisson structure. So we have a Lie group action and a Poisson connection, two independent structures on a given Poisson foliation. And the problem or the question is if we could find or construct a new Poisson connection which is invariant under the given G action, but related to the first connection in the following manner. So that there exists some one form Q such that the following relation holds. This is a very old problem. It was studied by Marsden, Montgomery, and Ratiu in the early 19th. They show that if the foliation is given by the fibers of a surjective submersion and the acting Lie group is compact and connected and acts by in a Hamiltonian manner, then we can construct this new connection gamma tilde by just taking the average of the original connection. So the G average of the original connection satisfies this relation. That's why they prove. And they were motivated by the fact that this connection appears in the study of phases in both classical and quantum mechanics. That was studied by Hannay and Berry, and that's why this class of connections were named by them after Hannay and Berry. This is the Hannay-Berry connection of the original connection gamma. On the other hand, this class of connections arise in the context of constructing invariant Dirac structures on foliated manifolds. Vallejo and Boroviev show that if we have the same hypothesis, but instead of having a Hamiltonian action, we have a locally Hamiltonian action, then we also can construct this connection adapted to the G action and to the original connection. This Hannay-Berry connection can be constructed. And the motivation for them, as I said, is to construct, to give an averaging procedure for a class of Dirac structures compatible with regular foliations. So what we are going to do here is to show first that this problem of finding this connection is in fact a cohomological problem in the context of the cohomology of Poisson foliations. And this also motivates another of the problems I'm going to discuss here is the isomorphism between the invariant cohomology and the cohomology of the Poisson foliation. And we are going to show also that we can construct a Hannay-Berry connection not only for locally Hamiltonian actions, but for a wider class of canonical actions. That's what we are going to do here. And if the time permits, maybe an application of this construction. So first, I need to construct this the cochain complex associated with the Poisson foliation. I have to recall that given a regular foliation, there are two algebraic structures induced by this regular foliation. First, for each p and q integers, consider this space of sections, which are multivector valued forms which value on leaf tangent multivector fields and vanishing along leaf tangent multivector fields. Here V denotes the tangent bundle and V0 the annihilator of this tangent bundle of the foliation. If we consider this graded space, if we take the sum over all P and Qs, here we have a natural grading given in this way for each K. The space of degree K is this sum. So here we have a graded Lie bracket, which is compatible with the B grading in the sense that if we take the Lie bracket of an element of B degree P and Q with an element of B degree P prime and Q prime, the resulting element has B degree P plus P prime and Q plus Q prime minus 1. And this is, it has B degree 0 minus 1, but it's a graded Lie bracket. And it appears in the context of foliations induced by surjective submersions in this paper of Krajnik and Fernandez. On the other hand, we have another algebraic structure. If we have the space of projectable vector valued forms, which are those that when evaluated on local projectable vector fields, the result is a local projectable vector field, we say that this vector valued P form is projectable. And we are dealing here with global objects. These projectable vector valued forms are defined in a local manner, but we are dealing with global objects. And it turns out that this class of projectable vector valued forms are closed under the Fröhlicher-Navier-Stokes bracket of the manifold. And again, this is a graded bracket in this, on this space. So we have in principle, two independent algebraic independent structures. But in fact, we have that the space of the degree P1 from the first algebra is an ideal. It uses is contained first on the second space, and the sum of all of them defines an ideal here. And this observation, and it can be formalized, allows to extend this to combine both brackets in the sense that we can unify them in a whole graded Lie algebra. So there exists a Lie algebra which unifies both graded Lie algebras, and it can be defined as follows. For P and Q with Q different from 1, we define BPQ by the space provided by the first B-graded Lie algebra. And when Q is equal 1, we take the projectable vector valued forms. And here we take the sum, and we have a B-graded space, but it has a graded Lie bracket, and again, it's compatible with the B-grading of B degree 0 minus 1. And also, it is natural with respect to foliation preserving diffeomorphisms. This bracket was introduced by Krajnik and Marcoux in the context, again, of foliations induced by surjective submersions. But again, this bracket can be also defined in the context of any regular foliation. So we are going to use this bracket to define the cochain complex associated with a Poisson foliation. So if we have a Poisson foliation, the Legendre-Poisson complex of the Poisson foliation is defined by taking the natural grading of this B-graded Lie algebra, and the coboundary operator is simply the adjoint of the Poisson structure. Recall that our Poisson structure is leaf tangent, so it is an element of this B-graded Lie algebra. It has B degree 0, 2. So it makes sense to consider the adjoint map. And by the Jacobi identity, it is a coboundary operator. And then what we are going to say for us, the cohomology of the Poisson foliation would be the cohomology of this cochain complex, the cochain complex given by this adjoint operator. And what do we have to consider this general Lie bracket? Why do we have to do so? It's because we want to come into play Ehresmann connections. If we have an Ehresmann connection, then we observe that the identity minus the Ehresmann connection is an element of, is a projectable vector valued one form, but it is not an element of the first B-graded algebra. And side remark is that the covariant derivative of the Ehresmann connection, which is a very well-known operator, can be simply described in this formalism as the adjoint of this element of this new B-graded algebra. And what we are going to use, which is very important, is the fact that an Ehresmann connection is Poisson on this Poisson foliation if and only if it is a the induced element is a cocycle of this Lie-Generowicz-Poisson complex. That's why the motivating problem from the beginning is in the context of cohomology, but it is not only for this reason, but it is important that the characterization of the Poisson condition is simply given as a coboundary condition. Now, let us consider again a Lie group acting on the Poisson foliation in a canonical and foliation preserving manner. Here, we consider the subspace of the invariant tensor fields, which, since the action is foliation preserving, turns out to be a graded Lie subalgebra of this B-graded Lie algebra. And moreover, since the action is canonical, then it is a cochain subcomplex of the Lie-Generowicz-Poisson complex of the Poisson foliation. So if we consider the cohomology of this cochain subcomplex, then we have the invariant cohomology of the Poisson foliation. And since this is the cohomology of a cochain subcomplex, there exists a canonical map between both cohomologies. In this context, a very natural question is the following. Under which condition this canonical map is an isomorphism? Under which condition I can compute the Foliated cohomology by means of the invariant cohomology? This question was already studied in the particular case when the foliation is given by the connected components of M. In this case, here we recover the standard Poisson cohomology of the Poisson manifold, and here the standard invariant cohomology. And this problem was studied by Ginzburg in the context of constructing momentum maps for actions of Poisson Lie groups. And he gives some conditions under which this map is an isomorphism. And we are going to show that the same conditions give the isomorphism property in the foliated case. So the same conditions which work in this particular case will also work here in the foliated case. That's what we are going to show. So we have to recall some properties, some basic properties about the actions of compact Lie groups. If we have a tensor field, its G average is defined by this integral, where here we have the normalized Haar measure of the compact Lie group. And since the action is foliation preserving, the G average take an element of VPQ to again an element of VPQ, which is G invariant. And since the action is canonical, then the G averaging commutes with the coboundary operator of the Lie-Generowicz-Poisson complex of the Poisson foliation. So the G average of cocycles is again a cocycle, and the G average of a coboundary is again a coboundary. And we can easily see that if the acting Lie group is compact, then the canonical map between the cohomologies is injective. It's very simple. If we have an invariant cocycle, which is a co-boundary with a possibly non-invariant primitive, then we can construct an invariant primitive just by taking the g-average. Here we use the invariance, then the property of commuting with the co-boundary operator, and then we got an invariant primitive given by the g-average of the original primitive. So the injective is very straightforward, but the surjectivity property requires more a few more things. But it's sufficient to get the surjectivity. It's sufficient to ensure the following property, that for every cocycle, it and its g-average belong to the same cohomology class in the Legendre-Poisson complex of the Poisson foliation. So that the difference between the cocycle and the g-average is co-boundary. So now suppose that besides compactness, that the Lie group is connected, and let's consider the Lie algebra G. So it is well known that there exists a full measure open set of the Lie group, which is diffeomorphic under the exponential map to an open ball of the Lie algebra around 0. And so if we denote by in this manner the infinitesimal generator of the G action, then we have the following infinitesimal formula for the G average of tensors. This formula holds for any tensor, not necessarily cocycles. Here, the integral over G with the hard measure is more precisely is an integral on this open ball on the Lie algebra. So here we have an integral on this open ball on the Lie algebra, which is diffeomorphic to a full measure open set of G, and here G varies along this open ball. And this formula was provided in this paper of Vallejo and Boroviov. Also, we need to consider or to restrict to the case of cotangential actions of Poisson manifolds. This notion was introduced by Lu and also developed by Ginsburg. So if we have a Lie group acting on a Poisson manifold, then a cotangent lift of a G action is a map from the Lie algebra to the space of one forms, such that the following relation holds. So we are here representing each infinitesimal generator of the G action by elements or by sections of the cotangent bundle. That's why we have a cotangent lift. In particular, the infinitesimal generators are tangent to the symplectic foliation of the Poisson structure. In the case when the G action admits a cotangent lift, it's said to be cotangential. And a very simple example is Hamiltonian and locally Hamiltonian actions. If we have a Hamiltonian action, then we have a momentum map, which induces a map from the Lie algebra to the space of smooth functions, and then the infinitesimal generator is described as by this formula. And here, if we set mu as the composition of the differential with the induced map by the momentum map, then we have a cotangent lift. A cotangent lift given which takes values on exact forms. Similarly, a locally Hamiltonian action means a cotangential action which takes values on closed forms, but we are consider any class of cotangent lift, not necessarily valuing on closed forms. In terms of the cotangent lift, the property for the action to be canonical is expressed by this condition. So the action is canonical if and only if this happens. So now, if we take into account a cocycle of the Legendre-Poisson complex of the Poisson foliation, then the Lie derivative of the infinitesimal generator is computed by the following formula given in terms of the cotangent lift. So if in addition we have this property, then this term vanishes, and then this Lie derivative is simply the co-boundary operator applied to this term. And this property, it trivially holds in the case of Hamiltonian and locally Hamiltonian actions, since mu is given in that particular case, but closed forms. So the main result, the first result, sorry, is the following: that if we have an action of a compact and connected Lie group on Poisson foliation such that it admits a cotangent lift satisfying this property, then for every cocycle there exists a primitive for the difference between its G average and the cocycle. So the cocycle and its G average belong to the same cohomology class. And this in particular implies that we have the isomorphism between the invariant and the foliated cohomology. And the proof is very simple if we take into account all of the previous discussion. Property 1 implies that the action is canonical and also implies this formula. So if we apply the infinitesimal formula we presented before, then we have that this difference is a coboundary where the primitive is given by this integral just by integrating this element. And here we are the fact that the action is canonical is used when we commute the coboundary operator with the pullback by the action, by this diffeomorphism given by the action. So the proof is straightforward. And before going further, let us describe how does this result works in the case of connections, of Poisson connections. So suppose we have a Poisson connection and a compact and connected Lie group acting on this Poisson foliation, and recall that in the case of Hamiltonian and locally Hamiltonian actions, we have a distinguished cotangent lift satisfying the property given by the previous result. So if we consider the cocycle associated with the Poisson connection, then the previous result says that we have this relation for some Q. If we rewrite this relation in terms of the Poisson connection, then we have this. So this explains why in the context of Hamiltonian and locally Hamiltonian actions, there always exists a Poisson connection of HANNAY-BERRY type. This explains the result of Marsden, Montgomery, and Ratiu for Hamiltonian action, and of Vallejo and Boroviev for locally Hamiltonian actions. It's because we have a distinguished cotangent lift satisfying this property. But what we are going to show is that we can, in the case of cocycles associated with Poisson connections, we can drop this condition. This condition is unnecessary, and this relation between the Poisson connection and its G average is always satisfied even if the action is not doesn't admit a cotangent lift with this property. So we only need that the action to be cotangential in order to have this relation. This is one of the goals of this talk. So again, let us consider a canonical and cotangential action of a compact and connected Lie group on a Poisson foliation. And in what follows, let us fix a projectable cocycle and a projectable vector valued one form, which is a cocycle of the cochain complex. And the problem now is to find conditions on the cocycle such that the difference between the cocycle and the G average is of this form, so that both elements belong to the same cohomology class. This is the problem now. And as I mentioned before, for cocycles induced by Poisson connections, this relation is always holds. This property always holds, but in general, this property will not be automatic. So in general, if we fix a cotangent lift, and also remember that the cocycle is fixed, if we define Q and L by this pair of integrals in terms of mu and the cocycle, then the difference between the cocycle and the G average is expressed in this manner. So we almost have what we want. Here the extra term is the composition of the anchor map with L. But if we impose that the cotangent lift and the cocycle satisfy this relation, then this term, the composition of P of the anchor map with L cancels out, and then we just have exactly what we want. So what we need to study now is to find conditions under which this relation holds, conditions under which one can choose a cotangent lift adapted to the given cocycle. So this first result says that this condition holds if and only if this differential form is Casimir valued, in the sense that when evaluated on local projectable vector fields, the result is a Casimir function. And this fact really follows from the canonicity of the action, from this relation, and also by the invariance of the average cocycle. By taking into account these three properties, we get this criteria. And finally, we also have this particular case. If there exists an Ehresmann connection such that the image of the average cocycle lies in the horizontal distribution of the Ehresmann connection, then the cocycle and its G-average belong to the same cohomology class. And to see this, we start with any cotangent lift, but then we observe that the composition of the cotangent lift with the dual map of the Ehresmann connection is another cotangent lift. But this cotangent lift has the following additional property, that this insertion, by definition, is zero, by hypothesis, is zero. And since since this is zero, in particular, it is Casimir valued, and then we have, by the previous lemma, the desired property, and both cocycles belong to the same cohomology class, given by the previous lemma. So when do we have cocycles such that this relation holds? When do we have a cocycle such that we can find an Ehresmann connection satisfying this property? Well, if the cocycle is the one associated with a Poisson connection, then we have this relation. And so we can extend the notion of HANNAY-BERRY connection to cotangential actions which are not necessarily Hamiltonian or locally Hamiltonian. And the fact is that for any Poisson connection, this relation holds for some Q. And in this proof, we just need to consider the G-average of the Poisson connection as gamma 0, and the cocycle is the one induced by the Poisson connection. So here, trivially, this composition is 0, and by the previous result, we got the proof immediately. So here, we just have to apply the previous result to this to the average connection and the cocycle induced by the Poisson connection. So here we have shown that on any cotangential and canonical action, not necessarily locally Hamiltonian, we have a connection of HANNAY-BERRY type associated with this action. And there are two applications I want to discuss. First, the curvature of the HANNAY-BERRY connection and an averaging procedure for Dirac structures compatible with Poisson foliations. So first, let us recall that the curvature of an Ehresmann connection is the obstruction to the involutivity or integrability of the horizontal distribution, and is described by this vector-valued two form, which is explicitly defined in this way. But if we use the graded bracket we introduced at the beginning of the lecture, it is given by this formula. We say that the curvature is Hamiltonian if it is a coboundary of the Ligenerovich-Poisson complex of the Poisson foliation. So if there exists a two form such that the bracket of P with the two form gives the curvature. If in addition one can choose this Hamiltonian form so that it is covariantly constant with respect to the connection, then we say that the given connection is admissible. And on the other hand, associated with the graded Lie bracket we introduced at the beginning, we have this derived Poisson bracket given on the algebra of differential forms vanishing along the foliation, along tangent vector fields. And this bracket is in fact the restriction of the derived bracket of this Lie algebra by minus p restricted to this abelian subalgebra. So this implies that this is in fact graded Lie bracket and is also a Poisson bracket with respect to the exterior product here. So we are going to need this operation in the following for the following result. So if we have a Poisson connection and a Lie group acting canonically and cotangentially, and we have the associated HANNAY-BERRY connection, then if the curvature of the original connection is Hamiltonian, also the curvature of the HANNAY-BERRY connection is Hamiltonian. And moreover, the property of being admissible is preserved by the G average. And the proof is very straightforward by using the Jacobi identity of this bracket. We use this relation for the curvature, this relation between the connection and the HANNAY-BERRY connection, and the description of the covariant derivative in terms of the bracket. And by straightforward computations, we obtain this relation. So if the curvature is Hamiltonian, then the other curvature is also Hamiltonian, where this sigma tilde is simply defined by this formula. Here we have used the derived bracket of we introduced before, and in a similar fashion we show that if this if the covariant derivative of sigma with respect to gamma is 0, then the covariant derivative of sigma tilde by the HANNAY-BERRY connection is 0. An alternative proof of this result can be given in the context of gauge transformation of coupling Dirac structures. This remark will be more clear in what follows. So now we are going to describe this procedure to construct invariant Dirac structures in the context of cotangential actions by means of the coupling method. This scheme to construct invariant Dirac structures was presented in this paper of Vallejo and Borovyov for the case of locally Hamiltonian actions. But since we have shown that we have this HANNAY-BERRY connection for cotangential actions, this procedure can be adapted to this more general case. So we are going to describe now the class of Dirac structures which we are going to apply this procedure. We are going to deal with coupling Dirac structures on foliated manifolds, which are those Dirac structures such that this sum is equal to the sum of the tangent and the cotangent bundle. So here we have like a splitting of this current algebroid in the sum of two Dirac structures. The main fact we are going to use about coupling Dirac structures on foliated manifolds is that they are in correspondence with triples of data p, gamma, and sigma, which consists of a leaf tangent Poisson structure and a Poisson connection on the Poisson foliation, a two form which is covariantly constant, and all related by the curvature identity. By this curvature identity. This characterization has been presented in the context of Poisson structures around symplectic leaves, also by Weissman in the case of Dirac structures on foliated manifolds, and also by Dufour and Wade while studying the local structure of Dirac manifolds. All these conditions can be simply summarized by saying that gamma is an admissible Poisson connection, where sigma is the Hamiltonian for the curvature. And in terms of the graded Lie bracket, all the four conditions can be summarized in a single one. if we define this element of this big-graded Lie algebra, we have an element of degree 0, 2, 1, 1, and 2, 0. So we have an element of total degree 2. For this element, all the 4 conditions are equivalent to this single equation. And this description was presented by Krajnik and Marcoux, again in the context of Dirac structures on 5-red manifolds. So here we have the following result, which simply says the following. If we have a coupling Dirac structure with associated geometric data p, gamma, and sigma, then the Dirac structure is invariant if and only if p and gamma are both invariant. In general, we would need that sigma to be also G-invariant, but by the previous relations, we can show that the G-invariance of sigma follows from the G-invariance of p and gamma. Here we just need to apply the G-invariance of p and the Jacobi identity, then the curvature identity here, then again the description of the curvature in this manner and the Jacobi identity, and the G-invariance of gamma. So here we have shown that this element is Casimir valued, and since the action is cotangential, the fact that this is Casimir valued implies that this element is J-invariant. So this is J-invariant for every infinitesimal generator, and since the Lie group is compact and connected, this implies that sigma must be J-invariant, and this assertion follows from the fact that follows by properties of the splitting of the Lie algebra of a compact Lie group, and also by the properties of periodic functions. Finally, we have the invariance. I present how to obtain an invariant Dirac structure for some class of Dirac structures compatible with the Poisson foliation. So we start with a foliated manifold and a coupling Dirac structure, and we have its associated geometric data. Then we assume that we have a compact and connected Lie group acting canonically and cotangentially, just as before, on this Poisson manifold. Then we have a Dirac structure, a new Dirac structure with the following properties. It is J-invariant, it is gauge equivalent to the original Dirac structure, and this Dirac structure is B-coupling, and its geometric data is of the following form. P, the left-tangent Poisson bivector is the same P. The connection is the HANNAY-BERRY connection, and sigma tilde is I will give the formula right away. So recall that by our previous result, the HANNAY-BERRY connection is related to the original one by some Q. Then if we use this Q and compute sigma tilde by this formula, then we have this curvature identity and this fact. So we have curvature identity, covariantly constant property. This is again a Poisson connection. So this triple defines or induces a B-coupling Dirac structure. And since P and the HANNAY-BERRY connection are J-invariant, also is this Dirac structure. And finally, the gauge equivalence between D and D tilde is given by this exact Q form. This in particular is a closed form. It has an associated gauge transformation, and this transformation takes D onto D tilde. So this is how we construct for a class of compatible Dirac structures on foliated manifolds an invariant Dirac structure, which is gauge equivalent to it by means of the fact that the original Poisson connection and the HANNAY-BERRY connection are related in this manner in the case of cotangential and canonical J actions. Thank you very much.